Hey guys, it's Miss Phoebus, and this is lesson 13, Function Stories. I like this lesson. This is a good lesson. So here are our learning goals for today's lesson, and what we have are the facts that we need to be able to differentiate between functions that are discrete and those that are continuous, and that you can draw or interpret the context of a situation by using a graph. So we're going to have different graphs, and we're going to be able to tell stories, or we are going to be able to have a story and be able to draw that as a graph. So our standard for this lesson is that for a function that models a relationship between two quantities, we're going to interpret key features of the graph. So we're going to have high points, we're going to have low points, things like that. We're going to identify what those key features mean. We also can sketch graphs showing key features given a verbal description of a relationship. We are also going to relate the domain of a function to its graph, and I'm not sure about the quantitative relationship it describes, but we're definitely going to be looking at how the graph, what is it doing in the domain. So we're going to look at discrete and continuous functions, and I've got some examples here. So on your sheet of notebook paper where you're taking notes, what I want you to do is I want you to draw, you're going to actually do two of these boxes. So I want you to draw a square divided into 4 pieces, but make it big enough so that you can write in each box. Label this one discrete functions. Now, discrete function, they are the result of something that is counted. So we are counting things when we're dealing with discrete functions. And what that means is that we're only going to deal with certain values. We're just counting things out. And when we count, we don't count using, you can use decimals, right? 1, 2, 2.5, 3. You can do that kind of stuff. But you're not going to count every single number in between, 2 and 3. So we're usually dealing with whole numbers. There are a few exceptions to that, but most of the time it's whole numbers. And so examples of discrete functions would be the number of pizzas ordered. When I call Papa John's and I say, hey Papa John's, I want 16 pizzas, they're going to be like, okay. If I say, hey Papa John's, I want 5 3/8 of a pizza, they're going to be like, what is wrong with you? You can't buy 3/8 of a pizza. What does that even look like? Somebody at the store ate 5 pieces. Do I pay for those 5 pieces they ate? It gets a little complicated. We're talking about whole number answers. And then if you're going to graph a discrete function, it's going to look like this. It's going to have a graph, and it's going to have dots. You can also do this on a number line, where you can have multiple pieces being used, but you're only using parts of them. You're not using all the spaces in between. All right, you're going to have a second box cut in 4. And then we're going to do the same thing, but for continuous functions. Continuous functions are the result of measuring something. And so when we measure, we're able to get all of those in-between values. So they deal with any value within a certain range. So fractions and decimals are okay. Irrational numbers are even okay because they are decimals. And then some examples, the weight of a baby. The weight of a baby, you don't say, okay, baby, you can either be 8 pounds or you can be 9 pounds. There's no in between. It's not happening. Usually you have, 8 pounds, so many ounces. The height of a tree, you can have fractions of a foot, an inch. Distance driven, you can have fractions of a mile. And so our graph looks something like this. Instead of dots that are disjoint, not connected, we have a line which is really made up of a whole bunch of points. All these numbers in between, and then see all those spaces? In between those spaces, there's even more numbers, and so that line is just a whole series of points, all so tightly packed together that they make a line. So that is the difference between discrete and continuous. And so when you're asking yourself, is it discrete or continuous? The question that I usually come to is, am I allowed to use fractions or not? And then, kind of in the case of shoe size, if I am allowed to use fractions, can every fraction be used? And if I'm saying no to fractions or no to not every fraction can be used, it's discrete. If I'm saying yes, I can have fractions, it's continuous. So let's look at some examples. I have two graphs here, and one of these graphs is discrete, the other one is continuous. So I want you to take a moment, I want you to pause the video and figure out which one is which. Which one's discrete, which one's continuous. So the one on the left with the nice straight pretty line, this is continuous. And then the one that's made up of the points, and there's even a point here, that are disjoint, not connected, this is discrete. Okay, but sometimes you don't have a graph. Sometimes you just have the wording of a situation. So let's look at the variables. Now we have independent variables. Independent variables are always the x, and the x is always the horizontal. So this is the independent variable, just in case that comes up. Variable, and this is the independent variable. And then the dependent variable is the y. So the y is the dependent. And we'll get more into that as we go on. But the y is the dependent. So x is independent, y is dependent. Now when you look at these, you should see, can you use fractions for one, both, none? I don't know. So let's see. Are you allowed to have fractions of time? Are you allowed to have fractions of hours, fractions of minutes, fractions of seconds? So yes, we can have fractions. All right, let's look at water in gallons. Let's say I have a bucket and I'm filling it up with water, or a swimming pool, I'm filling it up with water. Could I fill it up with partial gallons of water? I can. So fractions are okay here. So because fractions are okay to be able to be used in both of those situations, I'm going to have a continuous function. Now for my other problem here, what it appears, and we don't have like the actual wording of the situation, but what it looks like is, you know, if you get 0 problems right, you get 0 points. If you get 1 problem right, you get 10 points. 2 problems right, 20. So it looks like each problem you get 10 points. So let's think of it as like maybe a quiz or a test or something like that. Maybe it's 10 problems. It does not appear that you're getting partial credit, because if you got let's see, 4.5 problems right, you would, you know, be somewhere in that, you know, would you be right here? I don't, you know, it just kind of depends. So it doesn't look like we're giving any partial credit. So in this case, we are saying that no, you can't get a fraction. Fractions are not okay in our number of problems. The points, if you're thinking about them in terms of they're 10 points each, would you be able to get a 65? No, you would only be dealing in terms of 60. So you are definitely, or 60, 10, you're definitely only, you're restricted to certain values. In this case, your points will be only in multiples of 10. So if you're only dealing in multiples of 10, you are not going to be able to use fractions at all. And you're definitely going to be throwing out even more numbers there. So because both of those, you're not using fractions, and even with the points, you're even not even using some other specific values, you are in a discrete kind of problem. So you don't have to have the graphs. You can think about the situations themselves. All right, so let's get into our function stories. Now, most of our function stories are going to be continuous function stories, so that means that they're going to have lines, and these lines are going to have steepness. Some of them are going to be nice and flat, so if we have a line that's nice and flat, usually that means one variable is changing and another variable, our our independent variable is changing, our dependent variable is not. So something's happening, but not a whole lot is happening. Your steepness is going to indicate that something's happening quickly if it's really steep. So if I have a line that's really steep, something's happening quickly. If it's not quite as steep, it's happening just slower. So we are looking at steepness of a line. One of the things that I recommend you doing is kind of doing a little sketch in your notes. So I know that you're going to have to do a little bit of drawing. It doesn't have to be perfect, but kind of, pause the video, try to get this in your notes, and then we're going to go and look at this walk in a neighborhood. So we have three things. We can stand still, we can mark that with an S. We can walk quickly, we can mark that with a Q, or we can walk normally, we can make an N. So for standing still, time is going to pass. Look here, time is my independent variable. Total distance is my dependent variable. So when I am standing still, time is passing, but my distance isn't changing. So I'm going to have these flat horizontal lines. So right here, I'm standing still, but time is moving on. As I read this graph from left to right, it's moving. Standing still, but I'm making a mark. Even though I'm not moving, I'm making a mark in this graph. My distance isn't changing. And here is another horizontal piece, so time is changing, but my total distance isn't. So all of these, I'm going to put an S right here because it's connected to all three of these arrows, and that is going to represent standing still. All right, now the difference between walking quickly and walking normally is, of course, speed. And so if I'm walking quickly, I'm going to be able to go a further distance than I am if I am walking normally. So I want a steeper curve. So something like this piece right here is a lot steeper. This piece right here is also a lot steeper. And then even this piece is kind of steep. It might be more of a walking normal. Just kind of depends. But I really think that these are walking quickly. And I want to talk about the difference between that and walking normally. But I really do think that these pieces, kind of this piece and this piece, those are walking quickly. Because look at how this piece right here, it's not quite as steep as this red piece. I'm going to mark on it with green. It's not as steep as that piece. So this is our walking normally, and then walking normally here. Now, when I teach this lesson in class, I usually have a terrible story that goes along with it, and I'm going to share the same terrible story that I share every single year. This is a walk in the neighborhood. You ready? Okay, so this is a piece of my graph. I'm going to go over kind of where I am in black, because usually I point to it in the classroom. So I'm going for a walk in the neighborhood. I'm going to go and visit my friend. So I start off walking normally, and then as I walk normally, I hear the pitter-patter sounds of little feet behind me and a very mean bark. And so I realize the neighbor's dog is out. And so I start walking really, really quickly and try to get away from the dog. Why I'm not running, I'm not sure. But I'm walking quickly. Then I realize that the barking isn't happening. I mean, it's still happening, but it's not as close. So I turn around and I kind of look, and I'm kind of just standing there and watching, and I see the dog is behind the fence. The dog didn't get out. It's in the neighbor's yard still. It's just mad that I'm walking by, and so I'm just kind of standing there and looking at that. Well, I check my watch, and I'm like, I was supposed to be there 5 minutes ago at my friend's house. So I start walking quickly because I'm not running. And so I walk quickly until I get to my friend's house. And we're standing at the door and we're talking, or we're standing inside or something like that. And so see how this is a walk in the neighborhood. This is total distance. And this is, I'm going to go ahead and add this. This is probably total distance from my house. So on the trek up, I'm getting further away from my house. So I'm at my friend's house and we're talking. As I go back down, I'm going to have to head back towards my house so that the total distance I'm away from my house is getting smaller and close to 0. So while I am at my friend's house, I'm like, you know what? I think I left my stove on. I think I'm gonna go back home. So again, I don't know why I'm not running, but I'm walking quickly back towards my house, and then I stop and wait as the fire engines pass me, and I'm like kind of really scared. And so as I kind of walk quicker to my house and kind of maybe even turn the corner, then I can see my house is ablaze, it's on fire. And then this is kind of this last normal walking part. I'm in a daze going, oh, there's my house on fire, and watching the firefighters put it out. Isn't that a sad story? But anyway, do you see how I built a story and all the pieces made sense? I gave examples or reasons why I paused, I didn't move. I gave examples or reasons why I sped up. I gave examples why I turned around and came back. All the things, it's a terrible story, but I love it because it fits. So, it doesn't have to be the greatest story, but it does need to match what's going on in the graph. All right, so I've got another graph. I want you to sketch this out on your paper, and we're going to label what's going on. It has a nice title. It's about a pelican searching for fish. Our variables are time, so that's x. Usually that's what our independent variable is. Not always, but time. And then altitude is how far you are above the ground. So, or in this case, we're dealing with a pelican and they're trying to get fish. So we're not above the ground, we're above the water. So I'm going to make this water right here. What we have here is the starting point of this pelican's journey. And this piece, as it is increasing in altitude as time goes on, means that this is the pelican flying in the air. It's like a takeoff almost. Now it has a flat piece here. Time is continuing on, but its altitude remains the same. So this is a where it has reached a certain height and it is doing the actual searching for fish. So it is at like an optimal height. It is looking, it is scanning the water for a fish, and so it's kind of trying to stay at that same height, that perfect height for hunting. And then this piece, we have like a drop straight down. Now that doesn't usually happen, but what it's indicating is something happened really quickly. And what happened really quickly? This is where it dives for the fish. And then it goes into the water. And then after that, we're not sure what happens. I'm pretty sure that the pelican doesn't stay under the water, but that's where the story kind of stops. Like I said, it can continue on, but we don't have that part of the story. What we can see is the pelican taking off. We can see it searching for food, and we can see it diving for fish. Does it catch a fish? All right, now we're going to have a story given to us, and we are going to draw the graph. Now, how we choose to draw the graph is going to vary from person to person, but what we're going to notice is that it's going to have, I might draw my line steeper than you draw your line, but it should have the same kind of key features, indicated by the story. If you notice, I have time as my independent variable, it's x. I have total distance from the bottom of the hill, y. So I know that I'm doing something with a hill, and I'm going to read this story. So to take photographs of the area where you live for a school project, you ride your bicycle to the top of Lookout Knoll. Now we're riding a bicycle to the top of a hill. That's going to be a slow ride up. Okay? When you arrive at the top, you take a rest. So because we're taking a rest, that's that flat line. Time is moving on, but we are staying at the same height. So this is a flat line. On the way back down, because we have total distance from the bottom of the hill, so here we're going down the same road. So we're going down the hill. Do you think that that's slow or that's fast? On a bike going downhill, this is going to be a fast down. So we're going to have to make it steeper than the ride up. And then we're stopping to take more photographs. So we have another flat line. That's the end of the story. I don't know. You may live on this hill where you decided to take photographs for the rest of your life until you die. You could be there 15 minutes and go to the top. You could be there 15 minutes and go home. I don't know. We don't know what the rest of the story is. We can only draw a graph for the story that we have. So I want to show a slow ride up. So I'm going to do just kind of not, I mean, kind of flat, but it's not a very big, steep curve. So that is part A. This is my slow ride up the hill to the top of Lookout Knoll. If you make that piece longer, that's fine. This is my flat piece where I am stopping to take a rest. I'm going to label that B. On the way back down, so this is a fast down, so I'm going to do it steeper. I don't want it to go straight down, kind of like that pelican in the water thing. I'm not going to like be to the bottom of the hill like super fast. But I'm going to put C here. It's definitely steeper. This part is steeper than this part if I compare it. And then before I get to the bottom, I'm going to do another flat piece where I'm taking pictures. Do you see how I labeled them? Because those are in the story. It also looks like I went back uphill. This should be nice and flat. So make sure that that piece is flat. And you're trying to just figure out what is the story saying. How would you put that in a graph? I'm not measuring things. I'm doing it kind of a rough approximation. But if you make line A steeper than line C, you're going to say, well, riding up the hill was a lot faster than coming down the hill. That doesn't make sense. Or if line B and D weren't flat lines, they were going up at a different rate or down at a different rate. That doesn't make sense because we're stopping and resting. We're not changing our distance. So each part has a job, part of the story.